Okay, so now we're going to look at the rational root and then the factor theorem. So, what is the importance, first of all, of factorizing a polynomial in expanded form? It allows us to solve for x when the polynomial is equal to 0, because we first convert it to factorized form, and then we apply the null factor theorem. The rational root theorem and factor theorem are a really good set of tools that we can use to achieve that. So the first thing is, with the rational root theorem, it's this statement that for a polynomial equation, possible solutions are given by x equals d prime over a prime, where d prime is all the factors of d and a prime is all the factors of a. That's a typo there. So this is a bit confusing, but we can look at it with reference to an example, and that'll hopefully help it make more sense. So in this case, we have this polynomial here, 3x cubed minus 1. If we're looking for potential solutions to it when we set this polynomial equal to 0, then the solutions are going to have this form right here, d prime over a prime. D prime is all the factors of d. So in this case, our d value is 1. So all of the factors of 1 is, well, it's just 1 and negative 1. Because 1 times negative 1 is, negative 1 times negative 1 is 1, and 1 times 1 is 1. So 1 and negative 1 are factors of 1. Our a prime value here is 3. It could be 1 or 3, because the factors of 3 are 1 and 3. So we can do 3 times 1, or we can do negative 3 times negative 1. Those are all factors. So putting d prime, all our possible values of d prime over all our possible values of a prime, we're either going to get plus or minus 1. So that's going to look like negative 1, or plus or minus 1, that's the factors of 1, over plus or minus 1, because that's also a factor of 3. And so that's going to end up being plus or minus 1, as we see here. Or it could be plus or minus 1/3 by that same rationale, where instead our a prime value is 3, because that's a factor of 3. So we use the rational root theorem to just discover a couple potential solutions to a given polynomial, and that'll help us better guess the correct solution and save us a lot of time when it comes to substituting in random guesses until we find something that works. So the factor theorem is something that we use to make these substitutions. It states that for a given polynomial p, if p of negative a over b is equal to 0, then ax plus b is a factor of that polynomial. So again, it's helpful to look at this with reference to an example. If we have p of 1 over 2 is equal to 0 for a given polynomial p, then that means that 2x minus 1 is a factor of p. So what this means is we just substitute 1 over 2 in for x, and if it all ends up reducing down to 0, then that means that 2x minus 1 is a factor of that polynomial. Knowing one factor is really important though, because if you know one factor to a cubic equation, then you can separate it into a linear factor and a quadratic factor. And we know how to factorize quadratic factors down to their linear factors as well. And so eventually we're going to end up with a cubic completely in its factorized form. Okay, so one other thing we need to take note of is equating coefficients. So if two polynomials are equal, then each matching coefficient must be the same. And we've got an example there. X squared minus 4 equals ax squared plus bx plus c. If this statement is true, then that means that, first of all, the coefficients of the x squared terms are equal. So that means that the 1 out front here of this x squared term is equal to the a out front of the x squared term on the other side. That means a is equal to 1. Similarly, we can see that the x squared terms are going to be equal, and that tells us that b is equal to 0. In this case, you can imagine there being a plus 0x term here, and so that 0 is going to be equal to b. And then c is equal to negative 4. So now that we have all these tools in our arsenal, we can use this to fully factorize a polynomial. I've got a general set of steps here that I followed personally, and I would suggest that you follow it too because it really condenses everything down into distinct steps that are easy to follow. So first step is to substitute guesses for x until p of x is equal to 0. So again, with those guesses, we can use the rational root theorem to narrow down our guesses. Taking this example here on the right, we've got p of x equal to x cubed plus x squared, blah, blah, blah. Our possible solution for x, remember we take the possible factors of 24 and we divide them by the factors of the coefficient in front of the x cubed term, which in this case is 1. So in this case, we're just looking at all the factors of 24. So that's going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, 6, so on and so forth. Eventually, after a couple guesses, substituting these values in for x, you'll find that negative 2 is the value for x for which this polynomial is equal to 0. So p of negative 2 is equal to 0. The next thing we do is we use the factor theorem to rewrite the polynomial as the product of two factors. So again, looking on the right side here, since p of negative 2 is equal to 0, by the factor theorem, that means that x plus 2 is a factor. So we can rewrite the polynomial. First, we start off writing x plus 2, and then we know that there's a quadratic factor left, ax squared plus bx plus c. We don't know the values of a, b, and c, but we can then use our knowledge of equating coefficients to find those values. So we can expand this out, x plus 2 times ax squared plus bx plus c, and because it's equal to our original polynomial here, x cubed plus x squared, blah, 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 we can write this statement here, step 3, and then equate our coefficients. So a is equal to 1, you can see that there. B plus 2a is equal to 1, but because a is equal to 1, we can substitute that in and find that b is equal to negative 1. Using that same rationale going forward, we find that c is equal to 12. Then we can factorize the final quadratic factor. So we know what the quadratic factor is. We can substitute our values a, b, and c, and then we just finish off by factorizing that further into linear factors. And there we go. We've converted our polynomial from expanded form into factorized form. Again, I know a lot of this is confusing, so please make sure you're asking questions in the chat. Okay, we have a question. If x plus a is a factor of 4x cubed minus 13x squared minus ax, where a is any real number except for 0, then what are the factors? Okay, so I'm going to get my pen out here. Oh, what's happened? There we go. First of all, we need to rewrite this polynomial in a way that we can justifiably apply the factor theorem, because this is what it's asking us to do. It's asking about a factor. So let's write let p of x equal 4x cubed minus 13x squared minus ax. Okay. Now we can write if x plus a is a factor of p of x, then by the factor theorem, p of negative a, so because x plus a is our factor, we're taking negative a, must equal 0. I think there's a typo in the question. It should be asking prove that x plus a is a factor of this expression here. So p of a is equal to 0. So if we actually write out what p of a is, it's going to be 4a cubed minus 13a squared minus a times a. So this is going to be 4a cubed minus 13a squared minus a squared was 4a cubed minus 14a squared. Yeah, no, I've just realized the question should be asking find the values of a for which x plus a is a factor. Okay, so in which case, yeah, we're finding a set of values for a. We know this is equal to 0. So again, we can just factor out a squared as the common term here. We have 4a minus 14. So therefore, either a squared, and therefore a is equal to 0, or 4a minus 14 is equal to 0. That's applying the null factor theorem. Then rearranging for a, we're going to get a is equal to 14 over 4, which is 7 over 2. So those are our two values for a, for which x plus a is a factor of this particular polynomial. All right. We're now moving into some sketching practice. So we need to sketch this polynomial here. First of all, what form is it in? It's got brackets, so it's most likely in factorized form, and that would be true. So in which case, since it's in factorized form, the information it gives us at face value is the x-intercepts. In this case, we have the x-intercepts at x equals 1, because we have 1 minus 1 minus x. So if we set x equal to 1, then this would collapse to 1 minus 1, which is 0, and so the graph would be equal to 0 as a result. So x equals 1, and x equals negative 2, and the negative 2 just comes from the x plus 2 term. Y-intercept, we have to find that. So when x is equal to 0, we have y is equal to 1 minus 0 times 0 plus 2 squared. And that's just going to be, well, 1 minus 0 is 1. 0 plus 2 is just 2, so 2 squared, that's going to be 4. Okay. Turning points. Yeah, it might be worth doing the turning points too, just for the sake of completeness. Turning points. First of all, we find the derivative. Before we find the derivative, we need to expand this out. So I'll just do it up here. We have y equals 1 minus x times x plus 2 squared. So that's 1 minus x times x squared plus 4x plus 4, which is equal to, let's see, that's going to be x squared plus 4x plus 4 minus x cubed minus 4x squared minus 4x. And then if we collapse those terms down, we're going to get negative x cubed, what is that, minus 3x squared plus 4. Okay, so we have now this in expanded form, so now we can take the derivative. We have negative 3x squared. So remember, bring the power down and then subtract the power by 1. And then we have minus 3x squared here, so this is going to be negative 6x. And then we have 4, which obviously doesn't have, well, it has a derivative of 0. Okay, so at the turning points, dy dx is equal to 0. So therefore we have 0 equal to negative 3x squared minus 6x. We can factor out an x there. In fact, we can factor out a 3x there, so we get negative 3x. Oh, actually, we'll change that to negative 3x. So we're factoring out a negative 3x. Forget about that line. Let's just start a new line here. Negative 3x, we have x, and we have plus 2. Okay, so null factor theorem, x is equal to 0, or x is equal to negative 2. I'm just going to move my working up to here now. when x is equal to 0, y is equal to 4. We know that from when we found the y-intercept. And then when x is equal to -2, we know from our x-intercepts that that is going to be, oh, where's my pen gone? That's going to be y equals 0, because we have an x-intercept at x equals 2, right there. So we know now the turning points. We have one at 0 and 4, and -2 and 0. We know what the y-intercept is, y equals 4, and we know what the x-intercept is, or the x-intercepts are. So it's x equals 1 and x equals -2. Now note, one of the steps which I did was actually redundant, and that is finding the turning point for at the point x equals -2. Because if we look here, we have a quadratic factor, and if we go back to that particular slide, where is it? This slide here, it tells us whenever we have a quadratic factor, we're going to have a turning point. So going back to our question, this is information that we essentially already knew. Now, we can go ahead now and plot out our points and then plot out the actual graph itself. So we have a y-intercept at 4. We have that there. So I'm going to label this 0 and 4. We have an x-intercept at 1, which is right here. This is 1 and 0. And then we have an x-intercept also at -2. Something we should remember is this is a turning point as well. Now, remember the shape of a cubic is a mountain and then a valley, but that's for a positive cubic. In this case, we have a negative cubic, and the reason why that is because the x cubed term, all the way here over here on the top right, we found that it has a negative sign out front. So that means we're going to actually have a valley and then a mountain. So imagining how something like that would curve through these points, it's going to look something like this. So we're going to come down, hit that point, and then we have another turning point at 0 and 4. And then we're going to come down and go through that next x-intercept. So that's how you sketch a cubic polynomial. We have another question there. And this is in inflection point form. So we can immediately say there's only one turning point, and that's going to be inflection point. So let's write that down. Stationary inflection point at, and the coordinates are h and k, which in this case is -2 and 8. So I'll write that down here. -2 and, well, -2 and -8. So that's our h value and that's our k value. Okay, x-intercept. So we set y equal to 0. When y is equal to 0, we get 0 equal to x plus 2 cubed minus 8. And remember from that table we looked at, this is going to just involve rearranging to solve for x. So we have 8 equals x plus 2 cubed. Take the cube root of both sides. The cube root of 8 is 2. And the cube root of this expression is going to be x plus 2. So that means that x is equal to 0. Okay. Yeah, that looks right. Y-intercept. We set x equal to 0. So we get y is equal to 0 plus 2 cubed minus 8. And that's just going to be 2 cubed minus 8, which is 8 minus 8, which is 0. Again, this is a bit of a redundant information, because if we have an x-intercept at x equals 0, then that means that's also going to be our y-intercept. Okay, so let's plot out these 2 points. We have x and y-intercept at the origin there, and then we have our stationary inflection point at -2 and -8, which is going to be down here somewhere. So -2 and -8, and this is going to be 0 and 0. Notice that there's no negative sign in front of our x term here, which means that this is going to be an upright curve. And since we only have one inflection point, one turning point, and that is itself a stationary inflection point, it's going to have this kind of form. Oh, this is a bit hard to draw, but it's going to go through there, it's going to go through the origin there, and then it's just going to keep continuing up to infinity. It's going to look something like that. All right, so that wraps up our 1-2 revision on linear equations and polynomials. We're going to move into learning about other functions now. Please make sure you're asking questions if you have any questions about what we did there, or just any questions about what we've covered so far. All right, so the first type of function, new function we're going to learn about is the hyperbola. So this has the form y equals a over x minus b plus c. There's going to be a vertical asymptote at x equals b and a horizontal asymptote at y equals c. So here's the graph on the right of y equals 1 over x. Just note that depending on those values of b and c, it's going to kind of shift around, and then a here is going to dilate the graph, so it's going to spread it further away from the y and x axes. Okay, one thing you should know with hyperbola functions is you can use short division to convert it from one form to another. And this makes it a lot easier to work with. So in the previous slide, we looked at this form of a hyperbola, but this is also a hyperbola here. And we can use short division to convert it to this form here on the right, which is a lot similar to what we see in this equation we looked at here. So it's a more digestible form of a hyperbola. So the process for short division, you write out the fraction, in this case x plus 1 over x plus 2. What you then do is you introduce a plus 2 so that you mimic the plus 2 in the denominator. So now we have an x plus 2 term at the top, and we have an x plus 2 term at the bottom. You just want to make sure that you subtract the plus 2, so you write minus 2 in the numerator as well, so that the fraction is unchanged overall. What you can then do is split the fraction up into two separate fractions, and because you mimicked the plus 2 in the denominator, you can actually reduce this entire fraction down to just a number. So in this case, it reduces to 1. X plus 2 divided by x plus 2, it all cancels out to 1. And now we have something in the same form as what we looked at in the previous slide. A over x minus b plus c, 1 over negative 1 over x plus 2. Okay, so we'll get a bit of practice with this. I'm going to ignore the first example because it is pretty basic. We'll move straight into the second example here. So 2x minus 3. So we've got 2x minus 3, and we're trying to mimic the plus 1. But notice though that we have a 2 out here at the front. So in fact, what we're trying to mimic is a plus 2, and you'll see why later down the line of working. So we have a plus 2, and then, oh, that's supposed to be a minus. Let me get rid of that. So plus 2, so we added a 2, so we have to subtract a 2. And then we've got the minus 3 at the end there, and then we've got x plus 1. Okay, so we can then split it up. We have 2x plus 2 over x plus 1, and then we have plus, and then we have minus 2 minus 3 over x plus 1. Now notice with this first fraction here, we can rewrite it as 2 and then times x plus 1 over x plus 1. And now you can see there, because I chose to introduce a plus 2 in the numerator earlier on, I've actually ended up with two linear factors that I can just cancel out, and that's going to become a 2 in our next line of working. Here on the right, we're going to get minus 5 over x plus 1. So our final answer is going to be minus 5 over x plus 1. So there you go. Again, if you have any questions regarding that, please feel free to ask. We have a truncus now. This is kind of like a hyperbola, except with the hyperbola we had these curves here on opposite sides of the axes. This time they're kind of on the same side of one of the axes. In this case, they're on the same side of the x-axis. Uh, so it kind of looks like a volcano. You might be familiar with this from your previous study of 1-2. Same kind of rules as well as same kind of form for the equation. Just note that you have the x minus b term being squared. As opposed to hyperbola, there's no squared term. Again, vertical asymptote at x equals b, horizontal asymptote at y equals c. Okay, we'll look at some other functions now. First of all, we've got the square root function. So that's the root of x, or x to the half. It's going to have this shape where it starts at the origin. There's nothing on the left side of the x-axis, by the way. It just starts at the origin, then it increases, then it slowly gets flatter over time, passing through the point 1 and 1. If we have the cube root of x, or x to the third, you're going to have it pass through the origin and kind of have the same shape as a square root graph, except it also has this negative branch down here. So if you imagine what a cubic graph looks like, it's kind of just inverted, and that'll actually tie into what we learn about inverse functions later on. But just note that all the power functions where we have x equals 1 over a, and a is an odd number, in this case it's 3 because we have x to the 1 over 3, it's going to have this general shape. That's the same thing with x to the half actually as well. With this 2 here, if it's any even number, it's going to have this general shape where it's not going to have any negative branch. It's just going to start at the origin and go up and then peter out over time. Now, a general trend as we increase n is that the function is going to, the bigger n is, it's going to rise more drastically from the origin and then peter out over time. So we've got x to the half. You can see that it doesn't rise very drastically, but it still does rise, and then it takes longer to peter out. Whereas x to the 1 over 4, it rises very drastically, and then it slowly, well, it peters out a lot more quickly. Note that all of these graphs will pass through the point 1 and 1. So no matter what n is, whether it's odd or even, as long as it's an integer, it's going to pass through the point 1 and 1, as well as the origin. It's going to pass through the origin. Okay,